Okay, so today's lesson is a little bit different than our past lessons. It's like a history of physics lesson, and I took a whole course on the history of astronomy in university, and I'm sort of condensing that whole semesterized course down into one quick 30-minute lesson here. So let's do it. So back in the day, there were some old school rules. So this is what early astronomers knew for certain. They knew some things for certain. And this is a really bad way of doing science. You should never go into a scientific experiment with preconceived ideas of how things work, or else you can't really get away from those ideas. But they did this, and this is what they knew. So they knew that the Earth was the center of the universe. They knew that the Earth was at rest compared to everything else. And this made a lot of sense, right? If you lay down and you look up at the night sky, well, the moon moves, the sun moves throughout the day, everything's moving, but are we moving? No, right? We don't feel like we're moving, so this must be true. And they also knew that everything traveled in perfect circles because God created the heavens and everything was perfect, so they had to move in perfect circles. So this was early models of the Earth at the center of the universe and everything going around it. So these are famous people you need to know leading up to Kepler. So the first person to come up with the model of how the universe worked was Ptolemy. So Ptolemy came up with the first system to predict the motion of the planets, and his was a geocentric model. So when I use the term universe, I'm using it incorrectly. At the time, they thought the universe was everything that you see here. The universe we now is everything out in space with other galaxies and nebulas and everything out there. This is just our solar system, but they called it the universe back in the day. So Earth is at the center. Then we have Moon, Mercury, Venus, Sun, Mars, Jupiter, Saturn, and everything moved in perfect circles. The Earth was at the center of the universe, and then this out here were the heavens. And one of the ideas of what the heavens were, the stars, but what stars are is it's almost like a fabric, and then there's tiny pinholes in the fabric of heaven, and you can see the light from heaven through the stars. That was one of the ideas that what stars were. And now we know they're just hydrogen undergoing fusion, turning into helium, which is a little bit less romantic. So Ptolemy came up with this model of the universe, and what it failed to do was predict the motion of the planets accurately. So if your model is supposed to predict the motion of the planets and it doesn't do that accurately, it's not a very good model. So what he did was he needed to fix things, and he put in these epicycles. And what an epicycle is a sphere within a sphere, or a circle within a circle. And one of the biggest problems he had was the motion of Mars. So if you charted Mars along the night sky every night, so here would be Mars one night, here would be Mars another night, here would be Mars another night, so it's moving nicely, and then all of a sudden it goes backwards, so it says Mars is in retrograde. If you're into astronomy, or astrology I should say, you know about Mars being in retrograde, and you shouldn't do things during that time, but Mars goes backwards sometimes, so that couldn't be explained with his model. So he still stuck by those rules that he had where everything moved in perfect circles. So what he did is he put Mars within a circle within its bigger circle. So Mars could rotate in this circle as it rotated in this circle. He put all of them in there, and it fixed it a little bit. And then if you mapped out all the planets moving with circles within circles, this is what it looks like, and it was just a big mess. So he did this to explain why Mars moved backwards, but it didn't do a very good job. And what it's kind of like is that old clock in your car where every 6 months it sort of gets out of whack and it's like 5 minutes off and you have to reset it. And that's what Ptolemy's model was like. You had to reset it every so often. So nothing happened for a long time, nothing that anyone wrote down. But the next one that we're going to talk about was Copernicus. So Copernicus was the first person who suggested a heliocentric model where this was the sun at the center of the universe. He still followed those other rules, things traveling in perfect circles. At this time, the Catholic Church was in power, and if you came up with these ideas that went against their preconceived ideas, you would get in trouble for that. You'd get imprisoned. You'd get your books burned, things like that. So Copernicus didn't want to ruffle too many feathers, so he just made his heliocentric universe. So you can see the sun is at the center, and then here is Earth here, and then the moon orbits around the Earth, and then we have Mercury, Venus, Mars, Jupiter, Saturn, and then the heavens out there. Okay. So this next bigwig had a great mustache, and he wasn't someone who came up with models, but what he did was he had what's the word I'm looking for? Oh man, it sucks in these videos when you can't think of the word. He viewed the night sky every single night. Not a planetarium, but a observatory, that's what I'm looking for. They didn't have telescopes back then, but he used his observatory and he made really accurate observations of the planets. So this is Tycho Brahe, and he made extremely accurate observations of the movements of the planets and the stars. So why he was important is because if you had a model to describe the motion of the heavens, you could check it with his results. So if it's like, man, this is my model, is Mars going to be here in 2 weeks? And then you check his stats, it's like, yeah, Mars should be here this week, in 2 weeks, and then if your model predicted it, you know that you have a good model. So this is a video that shows Kepler's laws. It's kind of old, but it's good. It has lots of good information on it, so we'll watch that, and then we'll sort of sum up the information from that video.
This material has been excerpted from the college television course, The Mechanical Universe, and re-edited specifically for use in the high school curriculum. The Mechanical Universe is funded by the Annenberg CPB project, made possible by a grant from the National Science Foundation.
Johannes Kepler was a man in almost constant flight for his life. A life of illness and poverty, the loss of love and loved ones, witch hunts and the even meaner spirits of his associates. Simple existence was something of a challenge. Surely, no man ever sacrificed more to grasp the scientific truth. But on the other hand, no man's discoveries ever proved more rewarding than Kepler's laws. The law of ellipses, the law of equal areas, and Kepler's third law of planetary motion, the law of harmony. Around 1500, Nikolai Copernicus wrote a tornado of a book, The Revolution of Heavenly Orbs. Within these pages were ideas powerful enough to uproot and send the Earth hurtling through space, tossing aside the very foundation of physical science in the process. It was these ideas, however, that gave off sparks that fired the imagination of Johannes Kepler. He knew Copernicus had undermined the structure of the first great dictum of antiquity. And since the Earth was no longer the stationary center of the universe, Kepler was free to go around uniform circular motion. But what could take its place? Answering that question took the better and the worst part of Kepler's life, a journey with calculations that stretched from one end of Europe to the other. Finding the answer took everything he had and anything else he could borrow from his contemporaries. His was a hard road, but at its end the man called the wandering mathematician could describe the motions of the planets. Going further than Copernicus, Johannes Kepler had found the three laws of planetary motion. In 1618, 2 years after the Church warned Galileo to stop teaching such dangerous ideas, Johannes Kepler published a book called Harmony of the Worlds. Kepler not only attempted to unwrap and expose the secrets of the universe, he tried to tie up and explain them all. He struggled with geometrical models of planetary motion, but soon realized his astronomical data were not reliable enough. At the dawn of a new century, January 1st, 1600, Kepler set off in search of the most accurate astronomical data on Earth and the man who possessed them, Tycho Brahe. Tycho surprised Danish nobility with his decision to do something worthwhile. His penchant for astronomy became his reason for living, and for the last 38 years of his life, he charted the heavens with extraordinary precision. No one on Earth appreciated the potential value of Tycho's heavenly observations better than Johannes Kepler. To him, the data were essential, the key to unlock the door to the universe and to reveal what he called the secrets of the skies. But much to Kepler's dismay, Tycho knew how to keep a secret. So Kepler struggled without Tycho's precious data for almost 2 years. Then, on October 24th, 1601, fate stepped in. Tycho's dying words were, "Let me not seem to have lived in vain." The Danes' family withheld the data, but Kepler managed to make Tycho's last wish come true. Advancing science more than ethics, he stole the material. The otherwise mild-mannered little mathematician was finally ready, in his own words, to wage my war on Mars. Mars, the red planet. Mars, an early Roman god of agriculture and of war. Mars, through the ages, powerful and mysterious. Within the ancient world's concept of the Earth-centered universe, the planets moved in epicycles, and sometimes, as with Mars, the epicycles were very erratic. To account for such erratic behavior, Tycho conceived his own universe, the Tychonic solar system. Like Ptolemy, he placed the Earth at the center with the sun revolving around it. But like Copernicus, Tycho had the other planets orbiting the sun. While Tycho's system fit the appearances more simply than Ptolemy's, Kepler passionately embraced the views of Nicholas Copernicus. This was not only an unpopular view, Galileo would be tried in Rome for sharing it. It was an extremely difficult one to justify scientifically. Consider the Copernican solar system and the problems it presented Johannes Kepler. From Copernicus's revolutionary viewpoint, Kepler had to make mathematical observations from a planet that, rather than being central and stationary, was in motion with all the other planets. Imagine the difficulty of trying to compute the orbit of Mars from a moving platform, a platform that spins on its axis, in a non-circular orbit, with constantly varying velocity. and with an unknown center. This was Kepler's dilemma, and he approached it with a poetic faith in a logical universe. Do we ask what profit the little bird hopes for in singing? Kepler asked. Surely this question expressed his view of the purpose for which he had been created, to discover the secret of the skies. Just as some creatures seem to have been created to sing, Kepler seems to have been created to calculate. And his calculations, which totaled over 900 pages, were enormously difficult. His war on Mars was a patient siege in which many of his weapons were imperfect and faulty. But he employed them with a striking brilliance. For example, to find the location of his moving platform, Kepler used observations of Mars as it returned, Mars year after Mars year, to the same point in its orbit. Then he reversed them to find the orbit of the Earth. By finding a circle, even though it wasn't quite centered on the sun, Kepler had taken a step in the right direction. So now, once again, he attacked the problem of Mars. Still unable to find its exact path, he did manage to find something suggestive in its irregular speed. Mars moved faster when it was closer to the sun, and slower when it was farther away. This would become Kepler's second law, but he still hadn't found his first law. Approximately every 2 years, the Sun, the Earth, and Mars are in opposition. In other words, seen from either the Earth or the Sun, the position of Mars is the same. With another observation, 1 Mars year later, Kepler could triangulate a precise point on the orbit of Mars. Could a circular orbit, even one offset from the sun, fit all of the points? Almost, but not quite. That is, not within the unparalleled precision of Tycho Brahe's observations. What curve, then, would describe the orbit? The answer to that question revealed the secret of the heavens. With the sun at one focus, an oval orbit, a slightly distorted circle was called for. And that type of orbit was an ellipse. The ellipse, known to the ancient Greeks and finally rediscovered in the heavens by Johannes Kepler, can be viewed time and time again right here on Earth. It's simply a matter of looking at things in the right perspective. Any circle, viewed obliquely, appears as an ellipse. In the most graphic terms, a piece of string and 2 pins illustrate the simple elegance of an ellipse. Since the string doesn't stretch into a different length, the total distance from one pin to the pencil to the other pin is constant. A single point is called the focus. 2 points, the foci. The length of the semi-major axis is A. The semi-minor axis has the length B. The region bounded by the ellipse has area pi AB. The distance from the center to either focus is some fraction of A, EA. The symbol E represents the amount of eccentricity. As in the social context of the word, eccentricity means somewhat off-center. So when E shrinks to 0, when there's no eccentricity, the result is a perfectly rounded figure, an ellipse called a circle. But when E increases, the ellipse becomes increasingly eccentric and increasingly flat. Kepler's use of the ellipse for the orbit of Mars was possible only because it was the only planetary orbit eccentric enough, about 9%, to be noticeably non-circular. Had he waged war on any other planet, he probably would have died believing that circles reigned supreme throughout the universe. But of the battles he had an opportunity to choose, he chose well. And with Tycho's data, he was victorious in the knowledge that the ellipse, as perfect a fit as could be measured, was the mathematical secret of creation. These secrets were revealed, perhaps even paraded as the spoils of the war with Mars, as Kepler's 3 laws. Kepler's first law states that each planet orbits in an elliptical path with the Sun at one focus. As a planet moves around the Sun, the vector from Sun to planet sweeps out equal areas in equal times. When the planet's far from the Sun, moving slowly, it sweeps out an area in a certain time. When it's closer to the Sun, moving faster, it sweeps out the same area in the same amount of time. In 2 sweeping gestures, that's Kepler's second law. His third law came 10 years later. It states that the square of the period of a planet is proportional to the cube of the length of the semi-major axis, and it reveals a connection between the motions of different planets. In 1618, 2 years after the Church warned Galileo to stop teaching such dangerous ideas, Johannes Kepler published a book called Harmony of the Worlds. Kepler perceived that the ellipse is etched deeply into the grand design of the universe. Kepler's first law is the law of ellipses. All planets orbit the Sun in an elliptical path. The second law states that all planets orbiting the Sun sweep out equal areas in equal intervals of time. Kepler's third law, the law of harmony, states that the square of the period of a planet is proportional to the cube of the length of the semi-major axis.
This material is based upon work supported by the National Science Foundation under grant number SPE 8318420. Any opinions, findings, and conclusions or recommendations expressed in this program are those of the authors and do not necessarily reflect the views of the National Science Foundation.
So just a few terminology pieces that you might see in questions. I'm not actually going to test you on it, but you can see them in questions. Perihelion means the position of the planet closest to the sun, and aphelion is the position furthest from the sun. So Kepler's laws talked about how planets move in ellipses, and they said that there's two foci. So there's one blank focal point, and then the sun's at the other one. So that means that here the Earth is closer to the sun, and here the Earth is further from the sun. So this is aphelion, and that's perihelion. So let's sum up those Kepler's laws. So Kepler's first law states that planetary orbits are in ellipses. So they did a really good job of explaining ellipses and what that meant. So this is Earth in a circular orbit, and this is in an elliptical orbit. And most of them are almost completely circular. They have very little ellipses to it, very little eccentricity to it, but just a little bit. So we have the focus and then the sun at the other one. So Kepler's first law, planets travel in ellipses. Kepler's second law is the equal areas and equal times law. And what that means is this is when the Earth is closest to the sun. And when would you think that the Earth is closest to the sun? Well, you're probably wrong, because we're closest to the sun in December. And we're furthest from the sun in July. And you're like, what? Well, warming and cooling doesn't have to do with how close we are to the sun. It has to do with the tilt of the Earth. And this wouldn't make sense, because when it's December, when it's cold in North America, it's warm in Australia, so that wouldn't make sense with that. So it has to do with the tilt of the Earth, not how close we are to it. So this is how far we move in July, and this is how far we move in December. And if we took this area and we took this area, they'd be equal areas. But the more important part of that is, well, if we move this distance in 1 month and we move this distance in 1 month, well, it must be going faster in the winter and slower in the summer. So if planets can move equal areas in equal times, this means that the planets must be traveling faster when they are closest to the sun and slower when they're further away from the sun. This means that the Earth speeds up and slows down throughout its orbit. So that was the important part. Closer you are to the sun, faster you're going. And his third law is something that we're going to analyze a little bit later, but it has to do with the period and the radius of it. So this is the period of the orbit, and this is the radius of the orbit. But if you just look at this relationship, the units are in astronomical units in Earth years. So 1 astronomical unit is equal to this many meters. So they're in kind of weird units. You know what an astronomical unit is an astronomical unit is a distance from the Earth to the sun. So on average, the Earth and the sun are this far apart. So we are 1 astronomical unit away from the sun, right? So if we go 1 cubed, well, that's going to equal 1 squared, because that's 1 Earth year. But you can use it for other planets. You just get these weird units. So Mars is 1.532 astronomical units away. So it's a little bit further away from the sun. Calculate the period of Mars using Kepler's formula. Okay, so I'm going to switch screens here. It won't let me. There we go. So we're going to use our period squared equals radius cubed, and it asks us Mars is 1.532 astronomical units away. Calculate the period. So if we want to find the period, we have to square root both sides, and that'll get rid of that. So we would go 1.532 astronomical units, and we'd cube it, and then we'd square root it. So 1.532, and then to cube it, if you go into math 3 here, you can cube it, and then we'll square root our answer like that. So that means that the period of Mars is 1.896 Earth years. So that's how long it takes Mars to orbit the sun, is that many Earth years. And a thing you can think of that is, most of you are 16, let's say, yeah, you're 16-ish, so you're 16 Earth years old. Well, if you're in Mars, if you lived on Mars, it would take, I'm just trying to think of how to do this. 1 year, one Mars year is 1.896 Earth years. So if you want to find how old you are in Mars years, then you would just go 16 divided by this 1.86. Sorry, it was a little bit off the screen there. And if you're 16 here on Earth, on Mars you'd be 1.44. You'd be 8.5 years old if you lived on Mars. So if you wanted to drink, if you wanted to be if you wanted to be 18 on Mars, then you would have to be 34 Earth years old. So I still wouldn't be able to drink if I was Mars, if the legal drinking age on Mars was 18. Okay, so these are some questions. They're pretty easy. If you have any trouble with them, let me know and we can go through them.